Welcome. As it is the end of the week, I thought I would stitch together all the videos I've put together for the week into one long video to give you a better view of what the long-term evolution is. Let's first take a look at sunspots. This is the sunspot record as from the Royal Observatory in Belgium. The current sunspot number is 20. That's up from both yesterday and the day before, but overall the week the sunspot number has been in decline. Now let's take a look at some sunspot and magnetic movies. We're going to use the SDO HMI instrument for this. The continuum channel shows both the spots and also plage regions near the limb. The plage regions are these bright regions around the sunspots. They are remnants of old sunspot regions. Here we can see a large sunspot rotating off the southwest limb. Surprisingly, that region didn't produce much in the way of flares. We have another small region that is slowly decaying as it approaches sun center. It gets a few small spots, but then slowly disappears. And towards the end of this period, we get a new region coming over the southeast limb. There it is. And right towards the end, another new region coming up of the northeast limb. Magnetograms look like this. The convention here is that the white areas are magnetic field pointing towards you. The black areas are magnetic field pointing away from you. And you notice that they come in matched pairs. These are called bipoles. An active region or a sunspot region is a bipole, but there are a lot of smaller structures such as coronal bright points and things of that sort that are also magnetic bipoles. You will note that there are far more magnetic regions on the sun than there were sunspot regions. That is because not all magnetic regions produce sunspots. Only the strongest ones and the most active ones. For a region to be growing or changing rapidly is indicative that it's likely to flare. However, a region that is getting diffuse, pulled longer in the east-west direction, is an indication that it is decaying and will no longer be producing any significant flaring. Next, we'll take a look at prominences and filaments, because they form an important class of phenomena that result in coronal mass ejections when they erupt, and those can affect space weather and particularly give the Earth geomagnetic storms. For that, we'll use the 304 angstrom channel in the AIA instrument. That corresponds to the helium-2 line. Prominences are bright areas above the limb. They're bright because of contrast with the dark background sky, but when you see them on the disk, they are dark compared with the bright solar photosphere. Here we're looking at the transition region, about 100,000 degrees, 50 to 100,000 degrees, and we're looking at eruptions, particularly above the limb. You can see little jets here and there erupting above the limb, and these bright areas above the limb are called prominences. When they move onto the disk, they get dark. Now, in a second, you're going to see the image jiggle around. That was because the spacecraft was doing some calibration maneuvers. Just happened there. Now, shortly in the northeast quadrant, that's the upper left, you're going to see one of these regions erupt away from the sun. And it's going to be, interestingly, generally to the south, not radially, but to the south. Here it goes. There, you see it? That is a coronal mass ejection in the offing. Let's now take a look at the magnetic structure of the sun high in the corona, the so-called quiet sun. Now, if you look at these movies, you'll see that the general solar disk is anything but quiet, and some of the larger structures are very dynamic indeed. But nonetheless, we still call it the quiet sun. To do that, we look at 600,000 degree temperatures using the iron 9 line at 171 angstroms. The plasma, because it's charged, outlines the magnetic field. The magnetic field traps it. So you can actually follow the interconnections from one area to another. And you can see many of these are quite intricate. But some of these actually cross from the northern hemisphere to the southern hemisphere. And they're important because they actually form the basis for the evolution of the solar cycle from minimum to maximum, and then the decline in particular of the solar cycle and the reversal of the solar magnetic field. Now we're looking at plasma that's over 600,000 degrees Kelvin, so it's much hotter. And so we're looking above the transition region into the lower corona. This is supposed to be the quiet sun, but if you look at any area of the sun, you can see there's motion and changes all the time. You can also see that there's action at the limbs where solar active regions are reconnecting and changing all the time. One of the interesting features are these linear features at the poles. These are polar plumes and are open field lines where the solar wind escapes into the interplanetary medium. Also look at the northeast limb, that's the upper left. There's an active region coming over there, and there are some huge loops coming out of that region. Those loops are over 100,000 kilometers long. Next, we'll take a look at coronal holes. These are low temperature and low density phenomena, so they appear dark in contrast with the rest of the corona. We look at a somewhat hotter line here, just over 1 million degrees, and that's the iron 12 line in the AIA instrument. When the coronal holes reach the western hemisphere, that's the right-hand side of the sun, they can become geo-effective because that's the part of the solar disk that's connected directly magnetically to the Earth. That's because the magnetic field of the sun spirals out into the solar system. You can see a picture of it here on the right. So when we're looking at the sun, anything in the middle of the sun is not connected to us. But when you get to the western hemisphere, the right-hand side of the sun, it is better connected to us. So it's likely to be more geo-effective. It is interesting that a coronal hole is the absence of something and is therefore important. We can see two coronal holes here permanently, one at the North Pole and one at the South Pole. They're there most of the time. They disappear round about solar maximum, but obviously we're nowhere near that yet, so they're quite prominent at the moment. There's a couple of small coronal holes just crossing central meridian at the moment, but they're too small to affect the Earth. Just coming over the southeast limb, that's bottom left, there's a much larger coronal hole, and that's the one I've been talking about recently that will produce a high-speed solar wind stream that will impact the Earth. In fact, it did so just yesterday. Solar active regions are the bright areas that correspond to sunspots. You can see that in the iron 16 line at 335 angstroms. In this channel, you can see the high temperature coronal plasma at several million degrees. That shows active regions. And you'll again see there are more active regions than there are sunspot regions. So these are associated with the magnetic structures, and these magnetic structures can produce high temperature plasma in the corona even if there isn't a sunspot. One of the things that this type of observation could do for you is to see what's going on days before it actually happens on the disk. For example, if you look at the northeast limb, that's the upper left, you can see there's something bright coming over it, and it's at least 2 days before that sunspot appears on the disk. So this is a useful predictor of what's to come in terms of space weather. Speaking of flares, in the last week we've had 7 C flares from 2 different regions. 4 were on the 5th and the 6th of July, and then we had those 3 big C flares on the 9th of July. But overall, the X-ray background, the measure of solar activity here, has been on the decline too, along with the sunspot number. So to look at flares, we're going to use the iron 18 channel at 94 angstroms. Now we're going to look at a channel that is much higher in temperature, it's about 6 million degrees. So this is the channel to look at for flares. And any little brightening you see here is probably a B flare or a C flare. You'll note that even the smaller active regions that didn't produce sunspots have some high temperature material in them. So there's still energy being dissipated in these regions. Now, one of the things that you'll want to see is those 3 C flares. They occur after this jiggling around occurs, when that region in the northwest, that's about 2 o'clock, starts to flare. And here it goes. You'll see 3 bright flares. 1, 2, 3. Those are the 3 C flares, the C7, the C6, and the C5. As I said, there were 11 CMEs this last week. So to see those, we have to go to the LASCO coronagraph C2 field of view, the high resolution field of view. On the right here, we have a new sort of plot that I've not shown before. This shows when and where the coronal mass ejections occur. Most of the CMEs we've seen this last week have been off the west limb. So that's indicated by that blue arrow. Further round, you have another 2 CMEs that were off the east limb. The three that were associated with the C flares are shown here with the little white arrows. We're now going to take a look at coronal mass ejections, and there was one just off the west limb there to the right. And so most of the action we're going to see is off that west limb at the moment, if that diagram was anything over. There was a nice one off the west limb, and another. There's some smaller outflows, but I'm not sure whether they count or not. There's one, a big one. And here we go, 1, 2, 3. Those are the 3 C flares. And now there's a small one off another one off the west limb, but now we get one off the east limb. The solar wind has been relatively quiet. The vertical component of the magnetic field, BZ, dived south at one point during the week, which is usually an indicator of some activity occurring, but didn't really reflect itself in the solar wind. The density is still relatively low at about 10 particles per cubic centimeter. That increase in speed that was predicted as a result of that coronal hole, as seen here, we went up to nearly 450 kilometers per second, but that was not very fast. So we didn't expect to see a geomagnetic storm, and in fact we didn't. And also the temperature did rise for a short time to nearly 1,000,000 degrees, but again, not really sustained for any length of time. So it would be of low effect. During the week, the magnetosphere was relatively quiet. The KP index, which is a measure of activity in the magnetosphere, never rose above 3. 4 is considered unsettled. 5 would be a geomagnetic low-level storm. So let's compare how solar cycle 25 is doing with the equivalent period during solar cycle 24. In the year following minimum between solar cycles 23 and 24, 2009 had 206 spotless days. That was a 71% of the time. For the equivalent period between solar cycle 24 and 25, i.e. 2020, the number was 181 spotless days, and that was 50%. And most of that was in the first half of the year. Activity started picking up towards the end of that year and has continued into 2021. Sunspot number is rising about 20% faster in solar cycle 25 than it did during solar cycle 24, which would imply it's going to be larger. And we've had more and larger flares so far in solar cycle 25 than we had in solar cycle 24. So all in all, solar cycle 25 looks promising to be a much larger cycle than solar cycle 24. And you can forget any ideas of a grand solar minimum. So what conclusions can we draw from this last week? Solar activity is moderate to low. We've had 7 C flares, no M flares, no X flares. We had a total of 11 CMEs. We had no spotless days, and that now has stretched our consecutive no spotless day record to 66. We've had no geomagnetic storms in the last week, and from general parameters, solar cycle 25 seems to be outstripping solar cycle 24 and will likely be a larger cycle.